And I'll just leave it like this. Sure. Okay, can you guys see this?
Yes. Okay.
Cool. All right. So recapping a little bit from last time, I'm just going to kind of quickly go through what I went through the last time I was going through some of this stuff, since it's been about 2 weeks, and then hopefully this will set us up for the final week here. So once again, normalizing flows, what are they? Just a sequence of invertible and differentiable mappings that transform a known tractable distribution where both the evaluation and sampling are easy into another potentially complex but still valid probability density. So flow, in the sense, it's got this invertible differentiable sequence of mappings, and then the fact that we maintain this particular probability mass, right? Like we've got a normalized distribution, and we're ensuring that this final thing we end up with is also normalized. So a normalizing flow, right? So the relation between those distributions is just expressed by our change of variables formula. And this is just ensuring that our probability mass is going to be conserved during this transformation. So just make sure that those densities remain normalized. And so we're all familiar with this formula by now. So I can just take in a particular input, in this case, y, and once again, I apologize that my variables are all placed. Sometimes y is an output, sometimes y is an input, sometimes, so it just, once again, part of, drawing from a lot of different sources and putting this together. But yeah, so we can get basically assume your y is your data, right? And we've got this potentially unknown data distribution, or y, right? But we do have a potentially known distribution that's tractable, z. So the idea being, can we learn this mapping f theta that turns y into z so that we can, basically go, it converts between y and z, so that it allows us to basically take the data point we have, map it into a distribution that's tractable, where we can evaluate that probability and then transform back to our original data distribution. So basically, once again, as you can tell, it's been a minute since I've looked at this too, and my brain is still very foggy. So just doing my best for right now. But yeah, so essentially what we end up with is an expression for this potentially unknown data distribution by using one that is actually known and tractable. And so we can compose all these together. We can compose multiple flows together to make things very complex. So each one of these individual transformations doesn't have to be all that complex, in the same way that an individual unit in, say, neural network is just a basic logistic regression, right? It doesn't have to be all that complex, but by building up a bunch of these simple little building blocks, by building up a bunch of relatively simple flows back to back to back, you can actually get something relatively complicated. And each one of these stages is just going to add an additional volume correcting term into our for our Jacobian. So basically, after each flow, then you're either going to push up or you're going to push down a little bit on what that local probability density is. And keeping track of that from beginning all the way to the end allows us to arrive at our final goal with normalization intact. So here is our Jacobian with all of these, or sorry, here's the change of variables formula with all these different contributing flows. So each one is just adding an extra volume correcting term in here. So these flows can be trained with our usual maximum likelihood estimation, with stochastic gradient descent. We get just these additional contributions from the Jacobian. So training is not anything special. It's just a little bit of extra computation. We have a few requirements. We want X and Z to both have the same dimension. So as one constraint, our final, the space we're moving into has to have the same dimensionality as the space we started with. We need differentiability, invertibility, and we need that Jacobian determinant to be tractable. So the requirement 2 is not too hard. That's pretty standard fare for neural networks. And even the first one's not too bad, though that can quickly get into a cursive dimensionality kind of situation. But the thing that is really unique to the flows is requirements 3 and 4. So we need this transformation to be invertible, and we need to actually be able to calculate this Jacobian determinant. We need to be able to invert and calculate this determinant relatively computationally efficiently. Right? So the big catch on these flows is ultimately we want to design one that's highly expressive, easy to invert, easy to compute the Jacobian determinant. And what we end up with is we end up with a lot of trade-offs between this high expressivity and the ease and efficiency of computation here. We've got this little chart over to the right from that YouTube lecture I mentioned, which I hope everybody's watched. It really is good. It's excellent. But point being, calculating the determinant and calculating the inverse of a very large matrix is not a trivial affair. Right now, if we have constraints on the structure, then this can be made a little bit more tractable. So you can see, like, full matrix, you've got it's big O D cubed for both the inverse and the determinant, which is pretty gross. But if you're able to get the matrix into a diagonal form, then it's linear, right? So that's not too bad. So instead of this architecture first approach, last week, or I guess 2 weeks ago, I went through kind of a categorical approach to this. Instead of saying, oh, here's nice, here's real MVP, here's flow plus and glow and fjord, let's actually take a look at the general categories of approaches we're employing here, and that'll shine a little bit of light onto why these different architectures have employed the techniques that they have. And so this very, very closely follows this Kobizev 2020 paper, which I think I've also posted in the chat. Excellent survey paper on flows. And so we're going to go through a few types of flows: element-wise flows, linear flows, and then we're going to kind of tie both of those things together and look at the trade-offs here. And so I'm kind of making a distinction. You can have element-wise linear flows, and we're going to see that in a minute. But when I say element-wise, like the big constraint is saying, okay, we're just focusing on an element-wise transformation, but it can be extremely complicated and nonlinear. Whereas the linear flows, we're saying the transformation has to be linear, but we can take into account multiple combinations of variables, right? And so between both of these, this will highlight most of the big concepts we need. And really, we'll kind of finish it off with the autoregressive. And once we have all of that under our belt, then it makes a lot of sense out of things like coupling flows. Like, why in the world did it seems a little bit, even some of the students in the lecture were saying, well, why do you partition it like this? And that question gets kind of skated around a little bit. And so my goal here is to shine a little bit more light on that, elucidate the reasoning behind the coupling flows, and then some of the more complicated ones as well. So this isn't a comprehensive examination, but there's other approaches, and I'm probably not gonna touch on the planar and radial flows. I don't know, over the next week, my main goal is to finish up coupling flows. There's a few really nifty variants on the coupling flows as well. So I really just wanted to dive into the world of the coupling flows because it's pretty rich. And there is some interesting information on the residual flows. So I may touch on that along with the continuous flows. But that's where I really wanted to spend most of the firepower. Because you could spend a long time on this literature. So element-wise flows. So the idea here is you're going to apply independent nonlinear transformations to each element. So you've just got f theta of x. This overall transformation f theta of x is f theta applied to x1, applied to x2, so forth and so on. Of course, you could use parameter sharing, and this f theta could be the same across the board, or you could have that would be extremely restrictive. But you could also have separate, like an f theta 1, f theta 2, f theta 3, so forth and so on. So why in the world would you do this? Well, the big one is once again, same reason you do any of these constraints, which is to make the problem tractable. The Jacobian here then is diagonal. And so you can see this pretty easily. If we compute the partial with respect to x, you see, element 1, z1 depends only on x1, z2 depends only on x2, so forth and so on. So you've just got a diagonal matrix. And your Jacobian then is just going to be the product of, the determinant of the Jacobian is just going to be the product of these diagonal elements. So really the only thing you have to worry about here is making sure that f theta is easy to invert. Lots of choices here. And actually, this is something I really kind of wanted to touch on because I've done a fair bit of work myself on monotonically constrained neural networks. And so I found it very curious that things like the neural autoregressive flow, basically using neural networks, just monotonically constrained neural networks, there just doesn't seem to have been a whole lot of work on that. I saw 2 papers on it. And they're mentioned one of them's mentioned in the survey paper, but that just seems like a really, I don't know, I just look at the space and see a lot of very, very complicated approaches when I'm just like, the flexibility that comes with a neural network, like why not just use a monotonically constrained one? But anyway, hopefully we'll revisit that a little bit more next week. I just think that's fascinating. I think there's a lot of cool work that could be done there. Anywho, but point being, you just need to make sure that f theta is easy to invert. And so there's a lot of different choices for how to do that. There's the big problem here is that there's limited expressiveness. You're not going to be able to capture any correlations between the variables. The underlying assumption here is that all of the variables are independent, right? And that's, especially in the case of things like images, that's not going to work. But there might be a few use cases where this is doable. So, how do we bring other variables in? So here we're going to move into linear flows. The idea here is to say, well, let's just use affine transformations. Right? Super simple. And so basically, you just got, everybody should be familiar with this by now. It's just a very simple affine transformation. And it's going to be able to capture correlations between your variables, which you don't get with element-wise flows. It's super conceptually simple, just requires that matrix A is invertible. It's just going to shift and scale, the variables. So one of the big limitations then is if you start with an exponential family distribution, you're always going to stay within the exponential family. Like this is really not terribly expressive. The Jacobian, in this case, is just the inverse of that matrix A. Mainly, this is just a good conceptual building block. This is a way to kind of investigate the ideas, and you can think about how to make it more complicated later on. But if you understand the linear flows, then it's a lot easier to move into the more complex stuff with nonlinear flows. So it's very limited expressiveness, since a composition of linear transformations is just another linear transformation. And this is going to be very expensive to invert. If you remember that little chart from a minute ago, all this is big O d cubed. For both inversion and calculation of the determinant, and that's just, that's going to be bad for for a large number of dimensions. Because on every single training step, you're going to be calculating that determinant, right? So this is going to add up very quickly. So the question is, can we restrict the form of the matrix A to improve on this? And while we already just saw that with the element-wise, we know we can get a diagonal matrix with at least one constraint. So let's take a look at element-wise linear flows. Simplest, easiest possible thing. I'm sorry, let me see one. I just need to see something real fast. Okay, yeah. This is just the simplest thing possible. The idea here is to ensure that matrix A is diagonal. Because it's just going to be element-wise. So every x sub I is just going to be a function, or sorry, every z sub I is just going to be a function of x sub I, right? So z1 just a function of x1, so forth and so on. The transformation itself is linear, so it's very simple. And Inverse is, always going to be just linear, linear in the number of dimensions, and the determinant is calculating the determinant is also going to be linear in the number of dimensions. The Jacobian is just, this diagonal matrix, and so the determinant is just going to be the product of the diagonal elements. It does have a few uses, but the big reason is just to say, okay, let's look at the simplest possible thing we can do. So, but this is just super limited in what it can do. It's just not very expressive. So how do we improve? So we've started at the simplest possible thing, and how can we get a little bit more expressiveness? Right? How can we capture some correlation? Is there a way we can capture some of the correlation between the dimensions without it costing an arm and a leg? Right? Well, one idea is to make a triangular. So in this case, you can see that Z1 is going to be a function of X1, Z2 is going to be a function of X1 and X2, Z3 is going to be a function of X1, X2, and X3, so forth and so on. So this is going to be more expressive than an element-wise transformation. But the cool thing is the determinant is still just going to be the product of diagonal entries. And so this is very computationally efficient. The inverse is big OD cubed. So it's a little bit more expensive to calculate the inverse, but that's not such a huge deal because we're not going to be doing that as much as we need to be calculating the determinant. The determinant of the Jacobian is the real bottleneck here, and we can do that in linear time. So we got more expressiveness for effectively no additional cost. However, this expressiveness is contingent upon the ordering of the dimensions. So in this case, X1 is, or Z1 is only a function of X1, Z2 is only a function of, X1, X2. So that's not going to change. So you've kind of handicapped yourself a little bit here. And also it's still linear, but all of these are. So how do we get around this? So how do we ensure that we can get some more information into, say, X1, whatever the first ones are that have the very limited correlation, limited contribution from other variables in terms of correlations. So we can improve this using some permutation matrices. A permutation matrix is just going to allow us to reorder the dimensions with very little overhead. And it's going to improve the expressiveness of our triangular transformations when we use it alongside it. And this really doesn't add anything complicated. It doesn't really add much to our calculation, right? The determinant of the permutation matrix is just going to be 1. So, there's really no computation you can do there. And then, more general approach, we can use orthogonal matrices. The problem here is a sequence of permutations plus triangular transformations may still not be as expressive as just the unrestricted form. But, if we compose a whole bunch of these together, right, once again, you can have multiple, that's the whole point of these flow models. You can take a bunch of very simple transformations. So permutation, triangular, permutation, triangular, permutation, triangular, and eventually you can build up quite a bit of expressiveness, right? Finally, we've got factorization. So the idea here is instead of actually restricting the form of A, you factorize it. So you can see this here. This is just LU decomposition. So we've got P is a permutation matrix. L is the lower triangular matrix that just has ones on the diagonal. So that's just going to have a determinant of 1. Determinant of the permutation matrix is 1, and then U is then upper triangular with non-zero diagonal entries. And as long as the diagonal entries are non-zero, then it will have a non-singular. It will be non-singular, you've not really lost much. It doesn't seem at the face that you've really lost any expressiveness whatsoever, right? But we'll touch on that in a second. Determinant's just the product of the entries in U, because the other two are just 1, right? The inverse, once again, it's just an upper triangular matrix. The inverse is going to be B squared. This is very expressive. The big problem here is P, right? P is going to be discrete, right? It's a permutation matrix. So because it's discrete, that makes it very hard to optimize. And you're usually going to randomly initialize it. But if you go ahead and fix P, then you've constrained what you can learn, right? So in theory, this solves a lot of the problem, but in practice, it's hard to optimize that discrete matrix. So you still end up with some limitations. There's some stuff about QR decomposition is a better alternative. My point being, there are some options here. So quick intermission, quick summary. For nonlinear element-wise flows, it's super easy to calculate the determinant. Inversion could be potentially very expensive, especially depending on what you choose for your nonlinear transformation. And it has no ability to capture correlations between the dimensions. The expressiveness, therefore, is very limited. The linear flows, on the other hand, with various restrictions, the determinant can be very expensive to calculate depending on your restrictions. Inversion is generally going to be relatively easy. And the interdimensional correlations, yes, it can capture those correlations, but it also has limited expressiveness. But it has limited expressiveness for a different reason, which is the linearity assumption. So the nonlinear element-wise flows are limited because of the independence assumption. The linear flows are limited due to the linearity assumption. So we'd really like to, overcome both of these, right? Is there a way we can get, the nonlinear flows that are not element-wise, but also, very computationally tractable, right? So we want the expressivity and we want, tractable computation, but the nonlinear transformations seem to make inversion tricky. And to capture all the relationships between variables and transformation ends up making for an expensive Jacobian, generally speaking. But on the other hand, the independence and linearity assumptions limit the expressiveness. So how do we find the sweet spot? And that's really what all the rest of this is about. How do we find the sweet spot and use this idea of composing flows together to achieve our desired level of expressiveness without too much computational overhead? All right, so that's where we were last week. I know that was a lot, so I'm actually going to pause real quick to see if there were any questions. I know that version, that presentation, there was much choppier than it was last time.
Yeah, no, we looked at beginning of the homework, which kind of just showed us the composition for the two variables.
Hello?
Yep, no.
Oh,
looks good.
Sorry,
We looked at just the basics of the composition of flows last week in the homework, just the first assignment. So, yeah, it's a good refresher.
All right. Okay, on to autoregressive flows. So everyone hopefully still remembers the autoregressive models we looked at before. It was just all based on this idea of the chain rule, right? So you just get this ordered Bayes-net structure where you have the dependency between your variables is just followed. You basically have this ordered structure that you impose on it, and then you can have you can rely on that chain rule to calculate your probability, right? So here's a definition that Kobazev gives. So let's just assume we have some function h that maps all real numbers, just to the bijection parameterized by some theta. Then we have an autoregressive model that's just a function g that's mapping RD to RD, right? Where the outputs of each entry are conditioned on the previous entries of the input, right? So that's just to say that output T is just a function of the current input, and then it's parameterized by this conditioner that depends on your previous inputs, right? So the parameters at T depend on your inputs from T minus 1 back, and you take that together with your input at T, and that's how you calculate your Y sub T. So, but yeah, this theta sub T is just an arbitrary function that maps all the previous inputs to the set of parameters, right? So theta 1 is just a constant function, and then the others depend on what the previous inputs were, and we refer to these functions as conditioners, right? So the conditioner is just a function of the previous inputs. These are basically nonlinear generalizations of multiplication by a triangular matrix. So these are basically these nonlinear triangular transformations, and you can kind of see that, right? Because that back to the triangular matrix we were looking at, Z1 was a function of x1, Z2 was a function of x1 and x2. Here, we kind of have the same thing, like now that I've switched from Z's to Y's, I apologize, but Y1, sorry, Y2 is just going to be a function of x1 and x2. Y3 is a function of x1, x2, x3, so forth and so on. And so we basically get that same upshot that we got from the triangular matrices back on the linear flows, which was the Jacobian determinant is just going to be the product of the diagonal entries, right? So this is we get that, we get the cheap determinant and not too bad inverse calculation, right? So the idea here is that in terms of actually computing that determinant, it's going to be relatively cheap. So see that here. And so the first one we're going to take a look at is these masked autoregressive flows. So the masked autoregressive flows, the idea here is just we're going to impose some ordering on our inputs x sub t, and we're going to condition the tth transformation on the previous x's. That's pretty much the idea, right? So we just saw that. Why would you do this? Well, it's very highly expressive. I actually think there's a universality proof for at least some autoregressive models. So these are extremely expressive. On that forward computation to go from x to y can be parallelized. So training is super quick. Unfortunately, going from y to x is inherently going to be sequential, and so that's not going to be very efficient. Training then is fast, sampling is slow. So that was relatively quick. So I'm going to do a little animation here to drive this home. So let's say we want to do inference, right? So let's say we've got a sample, we've got an example, and we want to determine what's the p of x, what's the probability of that sample, right? So we've got x1, x2, x3. Well, we have this. We can immediately run that through because the conditioner is always going to be a function of just the x's, right? So theta 1 is constant, theta 2 is just a function of x1, theta 3 is a function of x1 and x2. And so we can just run that straight through. Right? So this is just one step, one pass through the network, and you can get your inference. Now let's say we want to do sampling. Right? Okay. Well, here, we got to start with Y1. And that's because all of those other conditioners are actually functions of X1 or X1 and X2. So we can't actually calculate the others until we actually have those inputs, right? So we have to start with Y1, and we can then get X1. once we have that, then we can calculate x2 because we need x1 to calculate, the transformation to go from y2 to x2. So this is one that's not necessarily appreciated when you just look at the static diagram. So you guys kind of see what's going on here, right? So to go from y2 to x2, we have to know x1. Then to go from y3, so now we can actually get y3, and to go from y3 to x3, we have to know x1 and x2, and so forth and so on. So this is why sampling is very slow from this autoregressive flow. So pause for a second. Everybody comfortable with this one?
Yeah, I think we covered this last time as well, right? I mean, the same, if it's good on the front, on the forward direction, but bad in the reverse direction, but you can now make another trade-off where it's, good on the backward direction, but now same, if you just invert the thing, right?
Right, and so that's where we go here. So we do a slightly different architecture. So the idea for the inverse autoregressive flows is we're going to condition on previous y's instead of previous x's, right? So now notice what has changed is our conditioner is not a function of x1 through xt minus 1. It's now a function of y1 through yp minus 1. So, why would you do this? Well, this is also still just as expressive as the regular autoregressive flow. But the inverse computation, as you just mentioned, can be parallelized. So this is very efficient from a sampling perspective. The problem is it's the forward pass is inherently sequential. So this is not very efficient. Training is then slow, sampling is fast. So this is the opposite issue from what we saw with the regular autoregressive flow. And this one, just looking at the diagrams, is a little confusing. And so that's why I like the little animation here. So let's start with sampling. So we start with let's go ahead and sample from our tractable distribution. So we now have our y1, y2, y3. Well, now once again, those conditioners are only functions of the y's, right? So we can immediately calculate our x's, right? So conditioner, the theta 1 is just a constant. Theta 2 is a function of y1. Theta 3 is a function of y1 and y2. So we can immediately go from our y's to our x's. Now, let's say we wanted to actually do inference here, right? Which we've got to do. We're doing training. Well, let's say we start with x1, right? And to get y1, that's pretty straightforward. Pass it straight on through. Y1 then is just, I forgot to reverse my arrows on this. Y1 is just a function of x1. That's simple. Y2 though, Y2 requires the knowledge of y1. Right? So that conditioner, theta 2, is a function of y1. So we couldn't calculate, we couldn't do the inference for x2 until we actually had have y1. Right. So you can see this here. If we actually want to calculate that, if we want to calculate y2, we need to have y1 and x2. Now, if we want to calculate y3, we're going to need y1, y2, and x3, so forth and so on. So this is where the inference is much slower. So it's a little bit odd, but you can just see the dependency structure here. So they're just as expressive as one another. Just one is faster for sampling, one is faster for inference. So obviously sequential is not the best way to go. That's relatively slow. And so then this brings us up to coupling flows, which I've not had a chance to really get through yet, having only really been better for about a day now. But basically, this is where we'd be going next. These coupling flows are effectively a trade-off, right, between our full autoregressive and our non-autoregressive flows. So whereas we impose that ordering for the autoregressive flows and said, okay, well, we're going to go through this very sequentially. Here, we're just going to partition and say, okay, this half is conditioning on this other half, right? And so instead of having to go through D steps, right, we only have 2 steps. So we condition B on A, and then maybe in the next step we're going to condition in the next stage in the flow, maybe we're going to condition A on B. And of course, we might want to make this more expressive using those permutation matrices. There's a whole bunch of things we can do here. But hopefully now you can kind of see why we're doing this, what the benefit is. Because in this case, you're still going to get that block triangular structure, which is going to give you a very cheap determinant. So yeah, so hopefully we can build up now. This is all the building blocks. You have the understanding of the element-wise flows, the linear flows, the different structures and constraints on those linear flows and what their pluses and minuses are. Then the autoregressive flows, and then how expressive those are, but then of course the trade-off then being the actual time it takes to step through the whole thing. So how do we balance all this? And coupling flows in their various forms are essentially the trade-off between all of these that are most popular. So we'll hit on this a little bit more next time, and hopefully I can finally finish this out. Knock on wood.
That's good stuff. Thank you, Jonathan.
Sure.
Thank you. Morten, do you want to look at few problems in the homework, or even probably just quickly look at last week's?
Yeah, sure. I prepared some more from the collab notebooks, so we can go through them.
Okay.
Yeah.
And maybe even like go through last week's as just a refresher, since you had some questions and whether that's been clarified.
Yeah. So that's where I wanted to start off with. So last time I was super confused about what's going on. I think it's like reading between the notation and all that is it's a little bit hard. So I'll try to. I think I figured it out. I haven't written it down. That's one of my tasks. Is I'll write this down properly into like an article, a short article. But I'll just go over what I think it's what's happening, and this is like between the notation and between the lines. This is probably like if you already figured it out, it's probably already obvious, but like it wasn't obvious to me.
Yeah, no, one more suggestions. I think in any of the fast AI type of courses, they encourage you to kind of blog about this. So I would say, yeah, if you are writing a note, you might even consider just writing a blog post, which while it may be obvious, as you said, to some, it will still be helpful to a lot more people making the journey like we did.
Yeah, I definitely want to. I'm going to write a blog post on it. It's okay. So this actually came. I was completely confused, and I actually had to read this part, the measure theory part, because this is like the most mathematically accurate way of describing things, right? So then, like after reading all this and then reading this, then it was like, okay, I think I know what's going on. But let me explain it, and then maybe I'm wrong, or maybe it'll be helpful to other people. So the basic premise here is that we have our data. I'll just draw some stuff here. How do I draw? Oh no, this is not working. Crop, pencil. How can I just draw it? Okay, this works. Okay, so we have our data, right? And this is our R of D. You can see my screen, right?
Yes.
Okay, great. So, and our problem is we have this data, we want a distribution of it, right? Like, how do we do this? So with flow, the idea is, well, I don't know how to do this, but I know normal flows, right? So, sorry, a normal distribution, right? So, so the normal distribution takes RD to R, right? So, if I you know, so here it is, like the normal. I'll draw the normal distribution. You know, it's not centered at 0. Sorry. But if and this is 1D. So but I know this distribution, right? So this is, you can just put the equation down and say and I know that, and I'm using normal, but in last homework it was uniform, but I'll get to that one. So we know this way, right? So we have RD, whatever dimensions we want. If it's 2D, I guess let me try to draw 2D. The 2D kind, you know, like the I'm not drawing it properly, but yeah, you know, you have that, but the output is 1. You know, it's always at R. You get a probability out of all of this, right? So so let me remove this. So the question, the actual what we're doing is, let's create a function called f theta that maps RD to R. And then because this already comes with a way to change this into R, into a probability, then we now have a probability function. So let's call this P. I'm probably using notation from different places, but and then so let's call data from data X, and this one, let's call it Z, and then the output is probability is Y. So it's kind of messed up, but the probability value is Y, and this dimension is called Z. And so we have this theta. This theta denotes the parameters we want to learn. So we take X and we transform it to D, and this has to be something called a diffeomorphism, which basically means a bijection and bijection. It just means that if I have this space, then I can take to this space, and I can go back and forth, and then the map F is differentiable both ways. Yeah. So diffeomorphism means slightly less, but let's just it's differentiable both ways. So they call this whole probability that we've just created new one called p theta. So this is a probability that given this set we can get a value in R. So that's called probability. So it's like a derived, or I forgot the name of it. It's here somewhere. They call it some sort of probability. Anyway, it's there's a name for it. But yeah, here it is. Push forward. Sorry. It's called a push forward probability. Basically, now we've created this way of saying we have our data and here's a distribution out of it, right? So as we can, but there's still a bunch of problems. So I'll try to go over it some more. So there's still some like confusing things here. But does this make sense, or how it's defined? So how I thought it was, this is the wrong way. What I was thinking was I thought like we would start with our X and RD, and then we would transpose it into some space R on the line. And then we're like, oh, this is not very good. Let's add more things to it, in the middle, and then kind of improve it. But that's not how the theoretical idea is. And the main problem, the main idea here is that this RD and this RD just has to be diffeomorphic. So in our case, it doesn't have to be exactly the same. It just has to have the right dimension. And so in the homework, there's the subtlety here, is that this probability is uniform. So this goes from 0, 1 probability to R. So it's a uniform distribution, but our images come from but our distribution comes from R, but this only comes from 0, 1. But there is a function that converts a real number into just 0, 1, right? So, but this F naught, F theta does exist. They're the same size, basically. The interval 0, 1 and all of real numbers, right? This and this are this are what, I don't know what the name is, but they're the same size. Oh, I don't know what you'd call it. So it doesn't have to be exactly the same, but just has to be the same size, right? So that's was the confusion, was like, how can you have a uniform that goes from 0, 1 to R, which is just the identity function here, because that we can get. But does this make sense? Like how this basic idea is formulated?
Yeah. So I guess so. Was the confusion how you have something where it's essentially a closed interval going to the all the way to negative infinity, positive infinity, or is
Oh, so the thing was that how could you put a uniform that goes from 0, 1 to R in here, right? So how does that make sense that this is uniform and this goes? So the thing is, this F theta now has to convert R, in our case, R, to the interval 0, 1, and it has to be diffeomorphic, right? And so obviously there's a obvious function, which is the CDF, right? So it takes it whatever value you give and pushes it between 0 and 1. And but here the CDF has nothing to do with probability. We're just being like super lazy and just using it. We could have just called this an exponential function or some other function that, there's nothing probabilistic about it. All we're using it here is to move R to 0 and 1. And then this 0 and 1, we have the uniform, so we can move it back into R. It's just like the way of thinking about it, right? So okay, so, right, so that was like one of the confusion, was like, okay, that's what's going on. Okay, so there was a couple more things that I was super confused about. Let me go through that one. So this is the main one, right? This equation. So you'll say, okay, we have X, we have F theta, and we have P. So Y should be just, P of F theta of X, right? Like that's all that's going on. You're just taking one item and just like you're just moving the functions around. Why is there this derivative here? So that confusion, like how does that make sense? So the intuition, the idea here, I can move it. Okay, so the idea here, why this happens, goes to the first slide. Is that, well, it also goes to the definition. Sorry, not the first slide, but this slide here. That P of X, it doesn't mean we're taking a function of a point. I mean, here the notation is terrible. This X and these X's are different. So this should be T and T. But just sort of like, but if we say P of X, that means that, let's say this X is 0.4, we're taking some size around it, right? Because in continuous, probability of a single number is 0, right? You can't say what is the probability of, some numbers. What's the probability of someone being 6 foot tall? It's always 0, right? But then when you say what's the probability of 6 foot tall, you're saying like, well, between 5'11.5" and 6 foot and a half, right? You're giving a small interval, right? With continuous ones, you always have to give an interval. So here, whenever you say P of X, this P of X, this P, and then P theta, we're not looking at a single value. We're actually looking at some interval, right? And so there's the notation. So P of X is equal to, AB. So using this notation, so can I make a new page here? Okay, new page, create, save. That didn't work. What is this one?
Well, sorry, quick question. So you're saying that
Sure.
The P and the P theta there, you're saying that those were intervals. Like, I don't know that we're necessarily looking at we're not trying to match a probability, right? We're just trying to match probability density.
But density means exactly this, that you have to have a set that goes through. Probability of a single point is 0 always, right?
Right, but the probability density it is 0 at any given point is well defined. That's what you have with that chart there. So that's why you have numbers that are much higher than 1, right? Yep. So you would never have a P, like if P of X was a probability, it would never be 4. That wouldn't make any sense.
Yep. So it would always be an integral. So you'd say, well, what is this for? But then you'd have this tiny little interval and you multiply it together and it would be like a small number.
Right.
Greater than,
so that's how you get the probability, right? So it doesn't make any sense to say what's the probability. Probability of any given point is 0.
Yep.
But to say the probability that a value X lands somewhere, like if I sample from that, what's the probability? I prefer to even like getting away from that and saying what's the probability mass between 2 points here, and then that's where you do what you're saying. You have to integrate. You have to look at the interval to get a probability. Yeah.
Yep. So the confusing part, sorry, maybe it's just the confused on my part, is that we're just composing functions, but then there's a determinant here. You go from X to F theta to P, but then how come you have a determinant? It's because there's a hidden integral in there, and so that was my point, was that P theta of X doesn't mean X point itself. You have to define what this X means. X means interval around it, or something else. You have to say, well, this X represents a set of similar things, or so this X isn't just a point, but it represents the set around it, or you can come up with any
X minus to X plus. That's often denoted between X minus and X plus.
I mean, I guess that's where my question is. So I think they really do actually mean a point there, because it's P theta isn't the probability. P theta of X isn't the probability of X. That is the density at that point. And so I kind of see this like it's that confusion between seeing like a probability density function. Then we go to CDF. CDFs actually do have a probability on the vertical axis, but that's just because they're looking at like what is the problem. Like there is an interval in that calculation, right? What's the probability of a point being from the far left end, or negative infinity all the way up into whatever your current value is. But if P theta is a probability density, then it doesn't make sense to just talk about X is a a point. You can talk about the density at a given point. Just so I guess what I'm saying is I'm not sure that that's supposed to be interpreted as probability as much as it's actually just a probability density, and that Jacobian then is, you know, relating how the mapping between those two densities is, you know, changing. But
yep. Yeah. So I guess, yeah. I can. So there's 2 points that I wanted to go. So in this equation that it shows, it's saying that x belongs to some interval, right? And again, this A and B, you know, we're thinking of like somewhere around it, but and then in the
but that's why he's using capital P there, right? Capital P is probability. So using the probability that x sits in that interval is the integral between those 2 points over that probability density function.
The distribution, this small p is the distribution function.
Right. So integrating, like if you go over to your chart on the left, like the probability that x is between 0.6 and 0.8, like say A is 0.6 and B is 0.8, then, you know, then that would be the area under that curve between 0.6 and 0.8.
Yep. Yep.
And that would be your probability.
Yep.
Right.
And so for this equation to make sense, then this p's are not distribution but density functions. So
Yes.
you're taking x as something surrounding x.
That's the part where you're losing me a little bit, but maybe I'm missing something.
Okay, so let me go to this point. Maybe this will make sense. Again, I could be wrong, but here, in the homework, so in the homework, he so p theta of x is okay, f theta of x, okay, this notation. So whenever you say what is the value of p of x, what set do you consider? So when you have an x values from your data set, which one are you considering? It's the CDF of everything behind it. So the interval here that they're used, AB, now becomes so
well, yeah. So if you jump back to that real quick, I think
sure.
in this where it might have been more helpful if you had more consistent notation. If you were to keep it capital P, right, then that would be, you could replace that that f theta of x and say that's capital P of x in, and then the interval would be negative infinity to, and I guess that would be kind of a strange notation. Maybe that's why it's not doing that, but it's the interval from negative infinity up to x, right?
Yeah.
So you're still, you know, integrating over that that one on the left, but that's why, you know, that vertical axis for the CDF is effectively a probability, right? Because it is summing up the area under the curve up into you get to x, right?
Yep. Yeah, this p of theta of x is kind of not the one that I have here. So this p theta of x is the okay. Okay, I said the CDF is the one that goes from R to 0, 1, right? That's the function. The distribution. What's going on? Pencil. So the distribution of this. Okay, it stopped writing. Okay. Save didn't work. I'll just do it. Sorry, let me just do another page, see if they will let me. Yeah, so this is our function that converts R to 0, 1, right? And so in their notation, p theta is the distribution of this CDF. So f theta, which is the same as this f theta. So this f theta.
So, and so when you say p theta, the distribution. So basically, p theta is the derivative of what you've drawn there.
No, yeah, it's a derivative of it. Yeah. So here, let's just do it this way. P theta. So f theta takes some number from here, from x, right? So when we look at a sample, it takes x, and then it's supposed to take RD to RD, which in our case is 1. So it takes this number and puts it in this number, right? And so how does it do it? And here's the equation for it. It takes the interval from negative infinity. Okay, this is not. So this x becomes the top x here from negative. So the interval is from negative infinity to this point in x, and you integrate over this distribution.
Mm-hmm.
So this x now becomes an interval from negative infinity until x. Does that make sense?
Oh yeah. I see where you're going. Okay, yeah. Now I see what.
So this x actually turns into an interval. So we have multiple choices, I guess. We have one where we could do this, and that's one of the things I need to do is make sure.
Can I grab on that 1 sec? Okay, so I think I see
Sure.
where you're going. Part of the confusion here is just once again, probabilities, CDFs, PDFs. That CDF, while it's true that in the strict sense that vertical axis is a probability, basically all we have is what that f theta is that's just an analytic. That's basically an analytic flow model. Like we've got an analytic function for it, right? You can call that probability, but we could also just say 0 to 1 is a uniform distribution, or we could treat it like that, right? So I think it's kind of like a sleight of hand, a bit jumping from CDFs and then saying, okay, well now let's pretend we've got a uniform on that vertical axis, right?
Yep.
So I don't like what I'm saying is like, you know, I don't know that it has to be a probability. Like we can just literally just treat that as, you know, I guess maybe that goes back to why it's kind of nice that it has f theta of x instead of expressing it in terms of probabilities, because what you have there is just, yeah, it just takes something that goes from negative infinity to positive infinity, supposedly, and squishes it into the interval 0 to 1. And we can just decide that we're going to impose a uniform structure on that 0 to 1, and then say, oh, well, look at that. Now we have a mapping from one distribution to a uniform distribution. But I think it's a little. I think I see where you're coming from. I feel like it's like, oh, well, look at this, and here's probabilities, and here's probability density functions, and then here's CDFs, and now suddenly we're changing the name of the game.
Yeah. So this is not used as a probability. It's just a function to change real numbers to.
It's just a mapping. Yep.
It's just a mapping, and they could have called it an exponential function, and you could have gone from 0 to 10 or negative 10 to 10, and then squished it back to or have a uniform that goes from negative 10 to 10 to 0, 1, right? It just adds layer of confusion. It's like
I think it's just abusing the notion of a cumulative density function, and I think it's it's like, here's the inspiration, and it's going to say, here's what a CDF is. Now let's use it for something totally different.
Yep.
Right. Yeah.
Yeah, because isn't it the case that if it is a probability, then the other restriction, besides being in the range 0 to 1, is the sum of the probabilities should be equal to 1.
Well, so it should still have
that,
right? Because if we just decided, okay, that, wouldn't that still be the case?
From a CDF to PDF, yes, but if you just make the thing normal on the y-axis, then I don't see why that would hold. Right?
So,
because if you're just sampling from normal, what is it to constrain you?
So
There has to be some constraint which ensures that a normal conversion from PDF to CDF and back, yes, because they are actual probabilities, and the probabilities have to obey the probability axioms or whatever, which are multiple, one of which is the sum of all the probabilities of the entire whatever range or domain has to be equal to 1. Right? So for a normal PDF and CDF, yes, but any just uniform, is that true?
Yeah, you can use anything. So I'll just say the bijection. This is the requirement, that is bijection and differentiable both ways. It doesn't have to be differentiable both ways, but let's just assume it is right now, because the linear one, obviously the coupling ones all violate this, but it's a bijection, right? So if it's a bijection, one of the things that, if it's bijection and it's continuous, then it must be what they call always increasing or always decreasing, right? You can't be bijection and if you dip like this, then obviously it's not a bijection, right? Because one point maps to two things, right?
So it just has to be monotonic, is basically.
Yeah, monotonic, strictly monotonic. It can't have this flat area. This flat area is like slowly going up. So there's no flat area here. So it has to be strictly monotonic. If it's discontinuous, it doesn't have to be. You can break it off and like, break this off in the middle and push it down, and you can have another one going this way. And so it's still, invertible, but it's not differentiable and not continuous at that point. But if it's continuous and it's bijection, then it must be monotonic. So you can take any monotonic function you want. You can just draw one, like, like as long as, that's fine. You can just, it can be anything. It doesn't have to be 0, 1. It can be anything as long as this maps, like this RD maps into the right kind. So here it was, R was all of R, and this was 0, 1. So if you wanted to, you could say R goes to -10 to 10, and then the uniform would be -10 to 10 goes into R, or this would be 0, 1 probability, right? So the point of being 0, 1, it's not even necessary. It's just that as long as you have some sort of increasing function, or at least piecewise they're not overlapping, then it's fine. You can go back and forth. You can take any. Does that make sense? Am I making things more confusing?
100%. That doesn't. Yeah, that you could have two continuous. You could have continuous to continuous, continuous to discrete, discrete to discrete. It doesn't. It doesn't have to be have that CDF structure. 100% correct. Yeah.
So so when we design the flow, I think there's two things that needs. Maybe this is obvious. So what does X mean? Like we have X. What does it represent in the set? Here in this case, it goes from -infinity to X. And in the first slide, he mentions, or one of the first slides, it belongs to some interval close around it. So this is not implemented. This one is not implemented. So I can test it out to make sure that if I do this, will it work or not? Will it still learn, or will it break? I don't see how other ways you can think of, but that's one thing. The second is just that which space are you considering? So second option is where did it go so far? Yeah, so second option is let me switch over. Second option is this consideration. What is the starting point, and what probability am I using? So if it's normalizing flow, you always use the normal distribution, so it's obvious. But here we're using uniform, so you can also use uniform here, which just maps 0, 1 to 0, 1. So it's the identity function here. Right, so that was some confusing part. So that's two things we have to worry about. And then the third thing is, okay, what is F theta that maps? And I think all of these are standard, like you just use normal, and then maybe this is just -infinity to the X point or some interval around here. So these are normal, and so only thing we talk about is the F theta itself, like how do we make a good F theta? But these two are sort of like behind the scenes here. And they were adding confusion to it. So here, this function F theta works on a set from here. So when we think about it, it's actually every element here is okay, this I can't write here. Okay, every element, if this is X, then it's okay, this is not working, sorry. If it's X, then it's okay, it's just so X is a set here. X is inside here, but whenever we say X, it's the whole region, and this gets mapped onto another blob here, which is f theta of X. And then the probability of this area is some number in R. So we have to think of it as sets being passed through. So that's why there's an integral, because you have to integrate over the whole area to get the so this is capital P, and then there's a smaller p, that distribution, so which you integrate over to get P. Right, and then there's more, like I think just the definitions of these way these things are defined is complicated. So, these are measurable spaces, and there's the sigma algebra, which basically means a set of all subsets that certain. So it doesn't say a number. This means like a set of all the subsets of it, a certain way of putting all the subsets, because obviously you can't have a set of all subsets, because there'll be a contradiction, right? So that with the there's a way you construct all the sets. So one of the things that you do is you say all the intervals, and you take the union of all the intervals that are possible, union, and then the intersection, or what union and the diff of them. And so the way it's defined is that it goes from a set to a set. And a measurable means it has a probability. And so the formal definition is like this, but then when we see RD to R, we think like, oh, we're sending points from one space to the other, right? But it's actually, there's the point turns into a set, and then that set, X is our data point, it turns into a set, and that set gets mapped onto a different set, and then the probability takes the area of the set with this density and goes to R, right? So does that?
Mochan, can you shoot back to the paper there for 1 second?
Yep.
Let's see. So I mean, so that mapping from RD to R, right? That's just so the RD is basically that's just the probability at a particular point. Like it's saying that it's assigning some probability density value to every point in RD, right? So I guess.
Yeah, this says something different than this. So, right. So this U means it's from a sigma algebra. It means it is a set. So G and G inverses are, the measure mu is the probability you're taking a set of it. So there's some like weird notation going on everywhere. So.
Right. I guess I had my questions. Where was the confusion or issue here? I guess I kind of missed that a little.
So if PZ is from RD to R, but it's this Z is, either this is a capital P, or this is not RD, or because if you put PZ here, then this PZ shouldn't be here. It should be capital P, or this should be the set of all subsets.
That's not a probability though, right? That lowercase p, I think they mean exactly what they have there, because oh gosh, I see what you're saying. That shouldn't be to R, it should be to no, because it is probability density.
It should be the sigma algebra of this. So all the intervals of R are of D. So I guess there's something.
I see. I think I see what you're doing. I think they made a typo.
Or you can think of it. So it could be another way of thinking is that, well, P, what is going on? P of Z Okay, this is sorry. How do I do this properly? Pen maybe. So P of Z is actually equal to the integral, 0 to Z of something. So you could say it goes from here it is RD, but then you have small p. You could
I
say,
think,
well, it's hiding inside here, but you're leaving this part out, right?
I think what they should have had in the paper was R plus. Like it's the that probability density doesn't all real number. It's not all real numbers, right? You don't have negative probability, or maybe in quantum mechanics, maybe in some like weird applications where you've got other constraints, but typically your probability density function is going to be zero or greater, right?
Yep. It should be 0,
otherwise
1.
Otherwise you admit the possibility of having negative probabilities, which doesn't make any sense. So that should be RD to R plus, and then that would make sense, I think.
Yep. Or 0, 1. So yeah.
Well, so not necessarily not 0, 1. I think they actually met R plus because the density can go all the way to infinity, positive infinity.
That's the distribution. Density means that it has to be between 0 and 1.
No, the probability density can go as positive as it wants to go, and you can shoot if you shoot back to the slides.
Okay, I think this one's called. Am I mixing up? This one's called
that's the CDF.
Oh yeah,
Cumulative density function. See, so there's the PDF on the left.
So this is the distribution, right? This is the distribution.
That's the P that they're talking about. So notice it can go all the way up to like 3 or 4, or you could even go all the way up to not quite infinity, but it could get very large. So I don't know. Maybe there's some weirdness with something like a delta function, but point being that could go very positive, but I don't believe it can go negative.
But that's not. So this equation doesn't make sense in that case because this is a probability. Okay.
It's probability density, not a probability, right? It's not.
Yeah. If it's
the CDF.
Okay. If that's the case, then it shouldn't have this determinant, because if this determinant is involved, there's an integration going on somewhere. But if you're just doing, if you're going from this to yeah, there's a.
You see, let me pull my slides.
Okay.
Look at those. I'm not. Let me see. I might have something in here.
Okay. Yeah, I think we can maybe discuss it a little bit more. I'll write it up so then maybe we can have a. But there's some good good points because here in this definition it says they're measurable spaces, so Z and Y will map from 0 to 1. It takes a set and puts it, but here either they're okay.
I guess what I fail to see is why that being a density makes the change of variables or makes the determinant of the Jacobian, or was it like what was the critique there?
If you have a determinant, there's a hidden integration going on somewhere, because you can only do a change of variable when there's an integral involved, right? So you're taking a number and then you're changing it to. So the other thing you could, that's the other thing I was thinking was, I don't know if we want to keep working this, but if this was small p, this is the density, and we actually moved x's over to densities, like and then we wouldn't have the grade we wouldn't have this, but we wouldn't be able to calculate the probabilities. Then we'd still have to take the integral somehow, and then we'd have capital P's around. So it would be a slightly different notation, but still could be done. But I think this is just the way they went. But I'll write it up more clearly. Then maybe we can. Yeah.
I think that might be helpful, but I think for at least the part that I would be arguing for is that PZ PZ, PY, everything they're talking about really are probability density functions, but that mapping to R should be the mapping to R plus. And given that, I guess I would have to see where the confusion would be, but that I think it should make sense if that's the case, or if you take it to mean that.
Okay, sure. Yeah, I think, yeah, okay. But
I think we need a whiteboard.
yeah, it would be good to argue about it because that's the only way I think it makes sense. So I can go back to some of the collab stuff. Where were we? Okay. And we can just look at some of the. Right, so this was the first one, fitting a 1D continuous distribution. We looked at it last time, and the confusing part was that the flow part, right? Yeah, so the base dist, what is the base dist? And then the base dist turned out to be uniform, right? Here, uniform from 0 to 1. So like, why is this the case? Because we discussed it, it goes from 0 to 1. And so when we do the flow, so you get the value x. And so what are we doing with this? We're taking a CDF of x, right? And the reason we take the CDF is because of this integration part. Oh, shoot, where did it go? Okay, this part. So f theta of x is negative infinity to x.
Before I think they're using the CDF there, just not necessarily because it's actually a CDF, but because doing that calculation that just gives you a mapping to to what you could regard as a uniform distribution.
Yeah. So then, yeah, this part makes sense. All you're doing is your z is just f theta. F theta is just this function here that maps to some point between 0 and 1. And there's weights involved because there's a mixture of Gaussians, right? So you have to add all of them up. Yeah, and then the log determinant, it's because of the yeah, it's because we need the determinant to calculate the log probability, right? So here in this case, here flow, you send x, and it just calculates the CDF and then the derivative part of it, which is the log probability. Yeah, takes the log probability, takes the exponential, multiplies it by the weights, and then takes the log of it again. I don't know if it's necessary to do, like, I don't know if you could just take the probability, or maybe this function isn't available, but you basically get the log determined, and then you go back to this equation, right? So py is equal to pz times the determinant, or one or the other, this one. And so where did it go? Okay, log probability, this one, right? So you take z, which you get it from the flow, which is just CDF, which maps your R into 0, 1, and then yeah, and then you get the log determinant also, and you just add them together, and you pass it to the base distribution. Since this is uniform, it doesn't do anything. The output is exactly the same as the input. Right. So in this way, this code makes sense, right?
Yep, that makes sense.
Okay. Is that okay? Can we move on to the next one then? Is there any? Okay. Yeah.
That's what we looked at last time.
Yeah, maybe this it's obvious, but it took a while for me to figure out like what's going on, because it wasn't obvious, especially like the first time you look at it. Like why is there uniform? Why is there no normalizing? The normal is in the CDF, and like it should be the other way around. What's going on, right? Yeah, and so the base distribution is the one, instead of normal, we use the beta distribution, so it also works. Instead of going from being the identity function, it becomes the beta distribution. I think we discussed what the beta distribution was. It has 2 parameters and all that stuff. Okay, and then this is the composition of flows to increase expressivity. We also looked at it, right?
Yeah.
So this
case was where.
Yeah, there's the trickiness happens. It's like, okay, okay, let me draw this. Hopefully this drawing still works. Let me delete everything. So let's. How does this not work? So we have X, and we go through F1 theta or F1 theta 1 comma theta. And then we go to Z1, let's say. I don't think that's the notation used, but this is between 0 and 1, right? So that's the problem, because we want another F2 theta, right? But then it takes from the entire R. So we can't do this because this is the wrong domain. So then we come up with this function called, where did it go? Yeah, this logit. Your domain is all of X, and oh wait, the other one. Wait, you can take any value. You can give any value from 0, 1. It maps to all of R, right? So this goes from 0 to 1, and then all of these map to all of R. So basically, this one, sketchpad. Okay. So instead of F2, we have logit of Z1, and then it goes 0, 1 to all of R, right? And let's call it Z1 star hat, right? Then we can say, okay, F2 theta. Does that make sense? Am I just making too much notation out of everything, or? And then goes back.
Yeah, and isn't the analogy to the activation function for the logit? I thought that's the explanation.
No, I think it's just to fix the 0, 1 problem. It's not really, maybe it's doing that, but from what I see, it's just to fix this problem that it's just to 0, 1 and it has to go back to R. We could say that it is, oh sorry, it is very sensitive here, and then once it goes close to 0, close to 1, it becomes very the value becomes very close to infinity here. So but
that's actually, sorry, just like a quick aside on that. One thing I was thinking about is, are some target distributions better than others, right? Precisely for that sort of reason. Like if you're trying to squish everything into a tiny little interval, right? Like it may be like, is there a benefit for choosing a uniform or a Gaussian or something more exotic in terms of actually being able to learn the distribution better, or maybe even having limits on how well you can learn it? I don't know.
Yeah, I think that
you can kind of imagine, like looking at that right there, like points that are out near the edge are that may be more difficult to tune.
Yeah, I think it's almost like if you're goes to 0 close to 1, then yeah, I'm not sure what it does. Maybe it is acting as a ReLU kind of like, or activation. It's pushing things.
Yeah, no, again, I didn't mean in a mathematical sense acting like ReLU, but at least from a, if you look at it architecturally, then the explanation of something is the combination of our basic, what we saw in the prior, where we put a layer and convert it from C, take the log determinant, convert the flow as well as it take the log determinant, and then that's not good enough, and then that's one layer, but then you have to add this mathematically for the reason that Martin you just stated, but conceptually, therefore, you can think of the first step and an activation and the combination being what's necessary to form a complete layer. And mathematically, what you're saying is the reason that's needed is because the first part takes you to 0 to 1, but to get probably the expressivity and so on, then you map it back. Mathematically, you need to get back to R, and that's the reason you have this alpha thing. So, and you compose many of these, and that's how you form layers, the composition of layers.
Yeah, so I'm a little bit.
At least that's how I consider.
The thing is that they don't use it when they do the affine transform, the affine ones, affine flows. They don't have anything like this because affine will just take you from R to R, or R squared to R squared.
Right.
R to,
right.
So
yeah.
they don't
so then,
use. Yeah, since they don't use it there, I think maybe it's not necessary. They're just correcting it, but it just says mixture. Yeah, 0, 1. We want to compose these flows to. We add non-linearity so that it says spreads the mass from 0, 1. I don't know. They don't use it for the affine. I don't know if you can add it in there and see what happens. And
no, actually, that makes sense, right? Because in an affine, you cannot add something that maps, because remember, the definition of affine is that it's linear, and if you add this, then it's no longer linear.
Oh, I meant
so it has to be kept.
I meant these ones. What were these ones? The kind of partially affine, like half affine, where the first one just passes through, but then the second one you have an affine to make it the triangular one. So I forgot what it's called, but it's just called NVP
okay.
here.
We'll look at it when you get.
Okay.
Yeah.
So it's I don't think it's used here. So there's I guess there's tanh and stuff, like maybe that's what does it. But then they have other stuff in there. So yeah, it gets yeah, and
Okay. Let's go back to.
Yeah. So all of this is that there's no neural networks here, right? So all it is just using gradient descent to tune all of these things, right? So in all of these,
but
we're not
neural
using...
networks in the sense of mapping of distributions using the one distribution to map to the other, and that being the flow concept, right? Because it's the mixture of CDF flow and then the logic, and then the mixture of CDF flow and then the logic.
Yeah, we can think of it that way, but the thetas themselves are directly manipulated by it could be because in the later ones they actually have. Sorry, go ahead.
No, I understand what you're saying about not being a neural in the traditional sense of how neural network is, but that's why I said this is more a conceptual analogy to look at it as, because you're just mapping from you're just flowing from one distribution to another.
Yeah, and the thing is that if you here the mixture of Gaussians has mean, standard deviation, and the weights, right? So there's 3 parameters for each of them. Technically, you could make a neural network, that takes in 3 and outputs 3, and you can have as many parameters as you want, and it could learn more things probably than just through gradient descent. So maybe that's where the neural network comes in, but yeah, but it has the same structure. But I think we looked at the sweeps and all of these, so there's the same thing. So there's not much going on here.
But actually, didn't we, if you go back, I think we saw that that particular stuff is more, trying to decipher how many nats per dim and how many layers are needed in order to extract, and it kind of showed that there's a limit beyond which it doesn't improve as you add layers and stuff, right?
Yep. So there's a number of layers and number of components. How many Gaussian mixture of Gaussians we're using, and how many layers we want to. Actually, when I ran this, the numbers came out different. So I don't know what was going on, but it was.
So
it was
you had different numbers. You're saying then what?
Yeah, it was slightly different. So this one, this is all yellow, right? It actually had some green ones and then some, slightly different. So maybe I ran it wrong, or or just the randomness creates a different one each time. But that was And so okay. And the next one was autoregressive flows. So we already talked about Jonathan already talked about autoregressive flows. I think here's the neural network here, that MLP that they use. So you give it the dimensions, the conditional dimensions, the number of layers, and then how many outputs it should be. And there's times 3 because we have the mean, standard deviation, and the weight. So when we're doing
last week, the thing that was a little bit, or we were trying to figure out what the condim did, or what that value is, correct?
Oh yeah,
and in this case, we always pass it in as 1.
Oh yeah, this one
because we are conditioning.
Yeah, it's one dimensional. So it was the I think we had different MLPs for. The idea was to use different neural networks for different dimension, different layer. So if let's see, flow somewhere. Yeah, the condition just goes into the MLP, and this was just 1, 2, 3, 4, depending on which area we're looking at. I think it's somewhere here. I can find it. Condition. How do you create the condition? Yeah, x1 is the condition. Yeah, it comes from the data. So what is the, so you have 2 values, right? X1, X2 for each one. Even though that's a picture, the actual data is X1, X2, a vector of pairs of a vector of pairs. I'm sorry, I'm thinking in C++, but it's a list of 2 numbers, right?
Tuples.
Yeah, tuples. Yeah, tuples of two size 2. And so so when you get the first one, I say, okay, the first one is 10. What's the second one? So you just send what the first value of the first one is as the condition. And then the neural network says, okay, I know that the first one was this. What's the, what should I output out depending on that? So if the first value is 1, then it has a different distribution than if it's 2, right? So it's the same idea. I think we use the same technique in the autoregressive, the MADE, similar idea. But I think the only, so yeah, the difference was that it would, instead of the neural network producing the actual probabilities, you output the mean, standard deviation, and the weight, and then you use it to do the mixture of the flows. So right, before it would just produce the output would be the n by n, right? So and each would have a probability. You would sorry, let me see if I can say so in this one, this goes from -1, let's say this is the one picture. So before it would produce, let's say with the divisions were 100 by 100, it would produce a 10,000 dimensional vector or a 100 by 100 matrix, each with a double, and then it was be each of them would be normalized to sum to 1 on each row, right? So, but instead we're producing the coefficients of the mixture models. Right, it's exactly the same, except instead of directly producing the probabilities, we're producing the coefficients of the mixture models, which then produces the probabilities. So I think there's less. You can maybe do the same thing with less. Does that make sense? I know this like borrows heavily from autoregressive. And oh yeah, and then the latent space. So I was like, what is this? What does it mean? So yeah, it basically is, where's the drawing here, latent space here. So you take the data set, right, and then you move it to Z. You flow it to Z. So it basically goes F theta of X and Z, and you're just plotting Z. So I don't know what plotting Z gives you, but there's an interesting thing that it you know since the last layer is goes into entrain and test. Okay, load flow demo 3. Okay, where is it? I wanted to show it somewhere. I don't know what the distribution is. So basically, it's getting it ready so that the Z distribution, so that the probability distribution at the end can make sense of it.
Yeah, isn't it also like building up I mean, the way I interpreted it is not just in this particular context, but it begins to build our intuition into what the latent space is as we move forward, so that, you know, potentially you could think of manipulating Z in the latent space and then getting the corresponding X's, which would then correspond to the image on the right?
Yeah.
I mean, here you can't directly do that, but I'm just saying that's kind of what the eventual manipulating of the smile on a face and all that does, right? It's you manipulate the Z and get to the X's.
I think, yeah.
Right? In this case, you can't directly do that.
Yeah. The actual the colors, the purple and the yellow, the neural network really doesn't know it, right? It's just doing the distribution of the two things.
Oh yeah.
But it's just showing that this is our original data, and somehow in Z space it's transformed into this, and then the last probability distribution can like you know, map all of this yellow part into the bottom moon, and then the top purple part into this moon. So yeah, and I guess we could, you know, yeah. So maybe when you talk about latent spaces, how to think about it becomes more clear. But like just from the mechanical point, it's just taking your our data set and mapping it to Z. But and as okay here, because we go from X to Z, but like what is Z? You know, what does that mean? So here in this space, that's our latent space. But what does that really mean? It's not clear. It depends on F theta, and also I guess it depends heavily on what P means. So yeah, so it's a little bit confused.
But isn't it? I mean, again, talking conceptually, it is shifting the distribution in the latent space to be able to better represent the distribution that we are actually after, right? We start with something, if you go up, whatever the distribution is originally, and then it begins to morph it to be able to, because it's just a blob originally, right? It's almost like, is it uniform, or where does he start from in this case?
Yeah, it's somewhere hidden here. I think it's here somewhere. I don't know what the autoregressive flow, what the mixture distribution. It's either Gaussian or it's logistic.
Oh,
so it's probably Gaussian, because logistic there's a they don't even have the right symbol for it, so it was giving some error to it. So it's probably just always normal. So yeah, but one thing you do notice is that it starts covering all of the Z space, right? So before it was just in this little space, but then with training, it kind of spreads out and covers all of it, and it's still neatly distributed. And depending on your neural network, what it learns, there's a separation, but it's not linear. So I guess it's the neural network decided this was the easiest way to separate it out. Maybe in the next chapter, latent spaces, it'll be better. So there's the face also. So this is the same thing with the face. They're not three classes, right? The neural network doesn't know anything about these classes. It's just for our labeling.
Yeah.
Okay. So there is the parameter sharing, which is a similar idea, but they share the same parameters. And this one is not 2D, but it's whatever dimension it is now, 20 by 20, so it's 400 dimensions. So this one has to use the we're almost out of time, but this one has to use the convolution 2D to do this. Right. So
okay. Interest of time, I think, like you said, maybe we'll start with next week we'll wrap up the flows by Jonathan can just finish up, and then we can start at this point and move forward.
Okay. Yeah, I was gonna. This is the interesting one. There's actually a video of it. The real MVP is the linear one, and you can. It's just like a preview of it. I will probably get disconnected, but this is the left, right, left, right, left, right. So you have these layers that. Left meaning the top part goes identity, and then the bottom part has a linear, and then the next one is the bottom part is linear, then the top part has the shift, and so you can do left, right, left, right, left, right, and it still does a good job, but it still does some weird stuff here. So it can't quite do it, but there's still the mixture of, I think, still produces the mixture of Gaussian somewhere here. But yeah, we can start continue with this one from next time. There's actually an interesting thing about what animation about what each one thing does. Let me just play it. It's just kind of fun, but yeah, it does take let's say a few seconds, but yeah, I'll write it up, the explanation. Maybe someone can read through it, and if it makes sense. I think it's sort of hidden between the notation, and it didn't make sense until if I thought about it, then all of it kind of clicks together, saying, okay, that's how they constructed it. So I'll write it up, and I'll get these other things ready, the faces and things like that. So this is the animation. Basically shows. So there's 6 layers. So in the face one, sorry. So this is the first one, the left one does. This is the right one. This is the left. This is the right. This is the left, and this is the right. So this is how it sort of like separates out the data in each of the layers.
That's super cool, and you can kind of see why it doesn't, why it's kind of smeared in that last one, because all it's ever doing is that it's like. See, you showed one a minute ago, and it looked like it was still kind of like smeared out. It didn't quite evenly separate. And I guess looking at this, it's kind of hard to see how the motions that it's going through there could actually create a nice clean separation.
It's because half of it just passes through, half of it is linear, right? So you can only do like move half the things around. So you can only like the first one, only the half of the face moves, right? And then the other half moves, and so it has to do with in that way.
That's really cool.
But
Interesting.
yeah, that animation, like it took me a while to get it working. But yeah, and so there's this one, and there's also the animation for the two moons, moon animation. Okay, and somewhere here. Yeah, and so there's other interesting things like the face thing, the face morphing, how we can be good and bad, and the checkerboard things like that. And yeah, and then this last one is just the quantization stuff. So, and then you can do the homework. I think that's all there is for the flow homeworks.
Okay, that'd be great. Yeah, maybe next week we can wrap things up. And week after I'll do the theory of variable.
I really like those animations. Those are really cool.
But you have to remember that the actual animation is, I can talk about it more. I probably will get disconnected, but it's a little bit sleight of hand. It isn't actually moving it that way. That it just, they're adding an effect to look like it's moving in an animation. But we can talk about it. So just the end result of each layer is there, but then they interpolate the animation to make it look like it's moving that way. So it isn't like each step it's moving, it's slowly that way. So this is the end result, and so there's a sleight of hand. So yeah, and we can talk about it more, but we have 2 minutes, so we'll probably get disconnected.
Great, thanks a lot, Jonathan and Martin.
Yeah, thanks guys. Thanks for watching.
Oh, no problem. Thank you, Jonathan.
Thank
Yeah,
you.
I'll put up the write up. Please, if you have time, just take a look at it and maybe give feedback if it makes sense.
Absolutely.
Sure thing.
Okay. Good. Thank you. I'll stop
Great.
the share.
Thanks a lot.
Thank you. Bye.
See you all next
See
week.
you guys next week. Bye.
Okay. Bye.